Okay, happy Tuesday, everybody. Such as it is. Tuesday. Yeah, question?
I've been looking at Eiler and I can't find your office hours
I don't. They should be in an announcement somewhere back there. Maybe 2 to 3, Tuesday, Thursday.
anymore. Oh, okay.
So, easy enough to remember, but there's an announcement back there somewhere, like in the first week or two, if you dig far enough. Let's see. So we've got today and Thursday, and then next Tuesday and Thursday, and then the following Tuesday, and then Thursday's the exam, and then break time. So we can kind of see what's there. We've basically got this week and next week to cover some new material, then we'll probably have a review day and then an exam that other week. So I don't know how far we're going to get. We're going to finish Chapter 7 today and get a little bit of a start on Chapter 8. I'd like to get through Chapter 10. I don't know if that's possible, and maybe it's just too much, but ideally it's like the first 5 chapters on the first exam and then 6 through 10-ish on the second exam. We'll see how that goes. I sent out an announcement just a little while ago. Your next homework is posted for Chapter 7, and it's due a week from today at 11:59. Okay? So I'm going to try to insist that you sort of stay on top of the homework. Too many people were doing it at the last second last go around, and I think that was reflected in the exam scores. So I want you to be working on the homework weekly, and as soon as we finish a chapter, I'll post a homework, basically do a week out from that moment, okay? Sound good? No, it doesn't sound good, but it's out there, all right? There's only 5 questions on this next assignment, so it's a little shorter. I think it's a little more straightforward. It should.
So you going to curve the older time with 5 questions?
I'm going to be generous, like extremely generous. Most of you are going to get 100 on those first few assignments. Most of you. As long as there was some semblance of effort, and it wasn't like you just like, bah, I didn't do it. So most of you are going to get very good grades on those assignments. So congratulations, you did fantastic. Bravo. All right. Let's see. So let me kind of back up a little bit since it's been a few days and remind you of what we were talking about. This idea of work. Work is essentially a force times a displacement. A force times how far the object moved. Just keep in mind, when you look at it mathematically, it's also got this cosine theta in between, which is essentially saying you can only deal with forces or components of forces that are along that same axis as the displacement. So, if it turns out that the force is perpendicular to the direction it's moving, well then that force isn't really contributing to the displacement. It's not doing any work. If it's perfectly in the same direction that it's moving, then all of that force is putting work on the object and putting energy in. And if it's pointing exactly opposite to the direction it's moving, then it's doing negative work and taking energy out. Okay? So we made it as far as answering a few of these questions, but we didn't really get to the peak point of the chapter. We didn't get to this point where we're dealing with the converse side of work, which is called energy. And you'll notice that I've set this up as sort of like a circular definition. Remember, work was the transfer of energy by a force. We're just going to say that energy is the ability of something to do some work. So really, these two things are kind of the same. In fact, they're so much the same that they even have the same unit. So the unit here is, again, the joule. And they're really just two sides of the same coin, okay? Work is transferring energy, and energy is just being able to do work. Just two different things from the different direction. So we're going to talk about 3 different kinds of energy. The focus of this chapter is on the first one. This second one is primarily in the next chapter. And this third one, I'm just going to introduce and just say it's later. I don't know if we'll do it this semester or if you get to it sort of next semester sometime, maybe even in the 3rd semester of the course. But it comes a little more later. I'm just going to tell you what it is, let you deal with it at that other time. So first of all, kinetic energy. This is energy that is associated with motion. If something is moving, we say it possesses kinetic energy. Thus the word kinetic. Okay? Something's moving, we say it has kinetic energy. We are going to focus for this point on one type of kinetic energy, which is translational kinetic energy. And we will typically just leave off the word translational, and it'll be assumed that's the type we're dealing with. And we'll save the word out in front for specifying other types. Okay? Translational just means motion from one place to another. Think of it just like the word translate if you're dealing with languages. You're moving from one language to another. Here we're just moving from a different type of thing to another. Okay? Translational actually involves the object going somewhere. So this translational kinetic energy is equal to 1/2 times the mass of the object times the velocity squared. 1/2 mv squared. That's the only type of kinetic energy you have to worry about in this chapter and the next chapter, probably the chapter after that. And so later on we'll cover another type. Translational kinetic energy. So if something has kinetic energy, well, it has to have the ability to do work, which means apply a force to something else and that force cause some type of displacement. So if you just imagine, well, kinetic energy is a mass times velocity squared. What if I'm just, moving? Yay, I'm moving this way, right? You can imagine that maybe I decided to just like, oh, I bumped into the table, okay? When I did that, I applied a force and it caused a displacement. The fact that I was moving meant I had the ability to do some work and apply a force to something else. If I'm just standing here, right, I don't have kinetic energy. Maybe I have another type of energy, but I don't have any kinetic energy that currently has the ability to impart a force and do some work, okay? So translational kinetic energy, I don't think there's anything complicated about the concept. If it's moving, it has kinetic energy. End of story, okay? Potential energy is associated with possible or potential motion. All of this sort of pivots around motion in one way or another. Potential energy is associated with possible motion. It's this idea of pent-up possibilities. Maybe something is ready to move. If I just remove all forces and give it the ability to move, it will. For instance, there's currently potential energy possessed by the iPad. The only thing that's preventing it from moving is the fact that I'm applying a force underneath it. If I remove that, it'll move. It's just waiting to happen, okay? So in this particular case, we're talking about one type of potential energy. It's potential energy associated with the fact that gravity wants to pull it. We're going to have multiple types of potential energy. Those are all going to come in the next chapter. At this point, I just want to give you sort of a feel for that option, okay? So in this particular case, it's not moving, but it really wants to, okay? Potential energy is essentially kinetic energy that's being held back. It's waiting to become kinetic energy, okay? Let's see, is there anything else I wanted to say about potential energy before I get to the third one? Let's just say there's multiple types of this that we'll deal with later. Right? Thermal energy is energy that is associated with temperature. I keep wanting to abbreviate the word associated, but I want to abbreviate it way too short, and I figured that just wouldn't turn out so well, so I'll just keep writing it. Every time I start, though, I'm like, ASS, that's about enough. Let's just abbreviate, and then I don't. So we'll keep it like it is. Associated with temperature. What is temperature other than, like, all of the components of matter? If you imagine their random vibrations and motion, as something gets hotter, all of that stuff vibrates and moves around more. As it gets colder, you say that those vibrations and those motions sort of freeze out. There's less of them. So really this is associated with motion too. It's just motion on a microscopic level. So you could sort of think of this as microscopic kinetic energy. The motion there is happening with atoms and molecules instead of the bulk substance itself. And that's really all you need to know about that for now. We'll do a little bit more later on. Okay? Kinetic energy is what we're going to focus on now. Potential energy later. Thermal energy much, much later. Okay? So let's see. By what factor does kinetic energy of a car change when its speed is tripled? I wouldn't expect you to think too long about that, because if I put in a 3v and square it, I'm going to get a factor of 9 out. So I'm going to have 9 times the kinetic energy. Okay, so if something is traveling 3 times as fast, it has 9 times the amount of kinetic energy. Let's see, is this one that I wanted to do? Hold on. No, we're not doing that one, because I want to hop over to this, which is going to kind of tie everything together, okay? The primary type of problem that we can work in this chapter connects work specifically with kinetic energy. And that's the work kinetic energy theorem, and you can see the way this connects everything. First of all, forces are the thing that does the work. A force is applied causing a displacement, so forces do work. But I just said it causes a displacement, and it's that work that somehow changes the motion of the object. Forces do work, we should say here, on the object. And as a result, this changes the motion of the object. And the motion of the object links right back to kinetic energy. How much is it moving? It's going to tell us something about how much kinetic energy it has. So this work kinetic energy theorem sort of links everything in this chapter, and we could write it something like this. The work is equal to the change in kinetic energy, so that's kinetic energy final minus kinetic energy initial. Or we could write it as 1/2 mv final squared minus 1/2 mv initial squared. All the same thing, but it really starts here with just work equals change in kinetic energy. Forces do work, and that work changes the motion, which we already talked about when describing positive and negative work, right? If you do positive work on something, well, I'm putting energy in, so you should imagine that as making it go faster, speeding up, giving it more kinetic energy. If I do negative work on an object, you can think of that as slowing it down, taking energy out, losing kinetic energy. And you see all that reflected in this equation, right? Positive work corresponds to this first term being larger than the second term. That's the only way I can get a positive. So that means that the final velocity is bigger than the initial velocity. Positive work, I made it speed up. If I'm doing negative work, then, well, this first term has to be smaller, which means it has to be going less fast at the end of the problem, okay? So everything we said about positive and negative work seems to really come out of this equation, as well as the whole cosine theta, which can be positive or negative. So 2 different ways of looking at the same thing. So what I want to do is 2 examples. 2 examples which, for the first time, will allow us to look at a problem in a new way when you already know one way to solve it, okay? So take a look at this problem. A watermelon drops from rest from a certain height and feels no air resistance. And if you look all the way down here, it asks for the speed of the watermelon just before it strikes the ground. There should be parts of your brain that are firing right now about how to solve the problem. Maybe like a list of variables, you know, pick one of your 4 kinematic equations, like all of that kind of stuff still applies. Meaning, it might be good practice to actually do the problem that way for starters. And I'm not going to do it. I want you to do that later. So maybe we set the ground as 0 and say that up is the positive direction. It starts from rest there at the top, and we know that top height. So we can say that this is 22 meters. It's going down to the ground. It starts at rest, so that's 0 meters per second, we're looking for that particular quantity, the final velocity. The acceleration is negative 9.8 meters per second squared, and the time is unknown. Okay, so we're saying that this is initial, right at the ground is final. You should know how to do that problem. If you don't trust yourself and you're thinking like, I don't know that I do, you should go home and try it. And if you have questions, you should ask me, or ask a friend, or ask somebody. You should make sure you work the problem, because the final exam is going to come around. You're going to have to work these kind of problems again. Okay? The thing is, doing it that way should give you the exact same answer as using all of this new stuff with work and kinetic energy. Okay? So, let's answer these first two parts, which really are just sort of, I don't know, precursors to part 3. We could go straight to part 3, get to the answer, and we'll do that on the next slide with another problem. But let's take it step by step. It says, calculate the work done by gravity on the watermelon during its displacement from the roof to the ground. So you might imagine that it's being displaced that direction. That's delta y. From the roof up at some level, 22 meters up, down to the ground. The entire time that's happening, it's being caused only by the gravitational force. Right? It's in free fall. That's the only force or the only influence that's on the watermelon. So we could find the work that's being done by gravity, and it's the force times the displacement times the cosine of the angle between those two. Work done by that particular force, which is the only work I can find because it's the only force, is the force times displacement times cosine theta. What's theta? Delta y points down, FG points down. What's the difference in the direction of those two? It's just 0, right? They're pointing in the same direction. So this is going to be 0, which means that whole cosine goes to 1. And then we have an equation for the gravitational force. You know this by now. It is what? Something times something. It's just mg. And delta y we know, so let's plug all those in. 4.9, 9.8, 22. Oops, left off a 2. You should get 1,056 joules. That's how much work is being done by gravity on the watermelon, and it's doing positive work, right? It's putting energy in because the watermelon's going faster and faster and faster. Okay? So if I want to find the watermelon's kinetic energy just before it strikes the ground, we can use the work kinetic energy theorem. It's equal to kinetic energy final minus kinetic energy initial. I just found the work. So it goes over here on the left-hand side. How much kinetic energy do I have at the initial point? 0. It's not moving. Has no kinetic energy. So that's going to be 0. And whoa, that just got easy fast. Kinetic energy final equals 1,056. Done. So far, this isn't too bad, right? Compared to, say, all the kinematic stuff. Yeah.
What's the reason why 9.8 is not negative?
9.8 being negative is all about direction, and this is all just scalar stuff. Work is a scalar, energy is a scalar. I don't care about direction. The magnitude of the acceleration due to gravity is 9.8. Anyone else? Think about these two answers. It's exactly the same amount. Okay? So this work that was done by gravity, remember, work changes the energy of the object. So the object started with no energy, and basically this amount of work went into the object. A positive work increased the amount of energy that the object had. So it makes sense that they should be the same. If we had to deal with air resistance, well then some of the energy would sort of get lost. Air resistance would take some of it away, and we wouldn't quite end up with as much in the object as the amount of work that I did. But we're not going to worry about a case like that until a little bit later, like next chapter, all right? So if I want to find how fast it's moving just before it strikes the ground, let's just use that final kinetic energy and solve for it. So 2 times kinetic energy final over m, and take a square root will give me the final velocity. So that's the square root of 2 times 1,056 all over 4.9. And you should get 20.8 meters per second. Notice I just got a positive. I know that it's going down, which is my negative direction, but it's not going to tell me that. This is a scalar. There is no direction information included, and I don't have to put any in, okay? If you work all of this over on the left, or excuse me, the right, wow, I've got issues, you should get the exact same answer by using kinematic equations. Try it later, okay? What do you think of that? Who says yay? If you say yay, say it. I can't get you to do it because all of you are like, nobody else is going to say it, so I'm not. Yay. Yay. This seems a little easier, maybe. Like none of the equations were terribly long. It's just like this, this, and this. Multiply a couple things and you're done. Yay? Yay. Okay, some people are whispering yay. I'll accept it. Let's try another one. Okay? A little red wagon with a given mass moves in a straight line on a horizontal frictionless surface. So we've got a flat surface. We've got a wagon. It has an initial speed of 3.3 meters per second. So it's moving this way with some initial velocity. And it's pushed a distance of 3.9 meters in that direction by a force. So there's a force that points in that direction, and you could say that it moves over here some distance delta x. Just based on this diagram, by the time it gets over here to the end of the delta x, is it going to be going faster or slower? It's already moving this way. I'm going to push it that way. When it gets here, faster or slower? Should be faster because work is what? Positive. Positive work. Notice the force is pointing in the same direction as the displacement. Positive work puts energy in, so it should have more kinetic energy when it gets done. So it should be moving faster. Okay? We can show that by using the work kinetic energy theorem. And we're going to go straight to calculating the final speed without doing sort of those little intermediate steps on the last problem, all right? So let's see, this is 1/2 mv final squared minus 1/2 mv initial squared. And the work is being done by that one force horizontally. It's the only force in the x direction. So let's see, we can write that as force times displacement times cosine of theta, which is again going to be 1, equals 1/2 mv final squared minus 1/2 mv initial squared. And we're going to solve for v final. So we just need to move a few things around. And I don't think anything cancels out, so that's all kind of sad. But let's see. So I've got f delta x plus 1/2 mv initial squared equals that other term. And then we'll say that v final is 2 times all of this. And then I need to divide by the mass and take a square root. And we have all of those numbers. So take a second, punch those into a calculator and see what you get. Let's make sure that we're all on the same page. What do you get for the final velocity? If you get a number that's less than 3.3, something's wrong. The wagon should be going faster at this point. I can wait all day. It's fine. I'm good. One of these days we're going to have like a calculation standoff. And all of you are going to talk before class like when he asks us to calculate. Don't do it. Don't break the picket line. Don't do it. And then we'll see how long you can hold up and how long I can hold up. And we'll just sit here all day staring at each other. It's going to be fantastic. I can't wait. Did you all have a good weekend? And a good Monday? And it wasn't long enough? And you wish it was still Sunday? Just think, pretty soon it'll be Wednesday, and the week will be halfway over again. And you'll be 1 week closer to dying. But that got depressing and dark fast. When you have the answer, just shout it out. Give me a chance to say, no, you're wrong. .54. Let's see. I like 4.5. It's bigger than 3.3, so unless we have any disagreements over that number, you both are in agreement. 4.06. You'll take, okay, yeah. All right, we'll go with 4.5. By the way, what if we had tried to set this up with kinematics? What would those variables look like? X initial, 0, X final, 3.9, whoops. V initial in the X direction was 3.3. V final in the X direction, well, I just found it, but I didn't know it originally, so that would have been a question mark. The acceleration would have been a question mark, and the time would have been a question mark, okay? So kinematics wasn't an option at the start of this problem. Now that I found the final velocity using this approach, I could go up there and find acceleration and time if I wanted to. We could connect all of this together, okay? Notice the second part of the problem says, what's the acceleration produced by the force? Again, well, you can find it up there, but we don't necessarily have to do that. Let me give you an alternative. So if I look at the forces that are acting on this object, I've got a normal force and a gravitational force, and this force that's to the right. That's it. It's frictionless. So that force F is the only force horizontally, which means I can say that if I add up the forces in the x direction, it's just F equals max, and I can quickly find that. F over m. So that is 10 over 3. Nope, that's not the number. Where is the mass? 8. There it is. Which is 1.25 meters per second squared. That answer should agree with what you get from kinematics, or something is wrong with your kinematics. Okay? So in a way, this single problem has new stuff and two different types of old stuff up there, all kind of mixed together. So this is going to be kind of the first time where I can give you a problem, and you can look at the problem and be like, ooh, I know there's more than one way to do this. And you might think, again, remember the other day when I drew the tops of the screws that nobody knew were screws, right? It's like, ooh, I could use my work kinetic energy screwdriver, or I could use my kinematic screwdriver, or I could use my force screwdriver. Now there's 3 of them. Which one is most appropriate for the job? Maybe you try to use the kinematics one and you find like, can't unscrew it with this. So you try this one and it gets it started, and then maybe you can switch back to the other screwdriver if you want to, all right? You've got options. There's different ways to approach these problems. So in general, unless I say you have to do it this way, figure out whichever way seems to get you to the answer fastest and take it. Why should you do more work if you don't have to, okay? And we're going to continue sort of expanding this where you have more and more ways to solve a single problem. Does anybody have any questions about either of these examples? Do you like them? Do you hate them? Do you hate that it's Tuesday? A little bit? Yeah? You're all better on Thursday. A little drab on Tuesday. Probably me too. It's just a little like, oh, are we going to get this week started? And then by Thursday, it feels like we're sliding downhill just a little bit. Right now, we're still climbing the mountain of the week. By Thursday, we're all happy. A little tireder, but happier. What do you do on Friday? You just skip all your classes, don't you? Wow, some people nodded way too quickly on that one. Like, yeah, you do. That's exactly what I do on Friday. Do you wish this class was Monday, Wednesday, Friday? No? Why?
Because my other classes are Tuesday, Thursday, so.
So you just don't do anything Monday, Wednesday, Friday but homework. Yeah. That and other stuff, yeah. There's always more to do elsewhere. I'm not saying you have nothing to do except school. I know all of you have lots to do. You would think the class would be shorter. Like, look at the clock. We'd only have like 18 minutes left if it was Monday, Wednesday, Friday. Now I'm making you wish.
3 hours a week.
It is. It's the same. Yeah, you just have to come more. So let's see. Some of these I want to do, and some of them I don't. Oh, hold on. Flipping through here. So I'm going to get rid of this one, and I'm going to get rid of that one, and I'm going to get rid of that one. But we're going to, that one's dumb too. There we go. Okay, so we're going to do these first. I think it was 4 that were back here. So 2 stones, one twice the mass of the other, are dropped from a cliff. Just before striking the ground, what is the kinetic energy of the heavy stone compared to the light stone? I'll write out the kinetic energy equation. And we know that that is twice as much. What can you tell me about their velocities just before they strike the ground? Good. That was a nice, fast answer. I appreciate that. So these are the same. The mass doesn't affect how fast they're traveling when they hit the ground. So just looking at that, it looks like we have twice the kinetic energy for the heavier object. Okay? And you just answered that question. What's the final speed of the heavy compared to the light? Those have to be the same just from things we've learned in the past. Okay? So if I have a child on a skateboard moving at 2 meters per second and a force changes the speed to 3 meters per second, what type of work is that? Huh? Positive, so that's a bit of a review question just to make sure you're still alive. But this is the one that we're going to spend a little bit more time on. So read it, take a moment to talk to each other and think about it, and then we'll discuss it and do it together. Go. Stand up and go find it.
Is there a formula that we need to know for this?
Work kinetic energy theorem will help you. work kinetic energy theorem, right? The braking force times the displacement has to equal the change in kinetic energy. And it's going from having some kinetic energy to stopping, okay? So it has no final kinetic energy. So what we're saying is that whatever this kinetic energy is that it's starting with, this needs to do negative work to get rid of it, basically, okay? So if I double my speed that I'm starting with, how much bigger is my kinetic energy?
4 times.
Yeah, if I double it, it gets squared, so I've got 4 times the kinetic energy as what I had before, which means I need to do 4 times the amount of work, but the braking force is the same. So this is the same, and we need 4 times the work. The only way I can get that is by having 4 times the displacement, okay? So that means I've got 4 times delta x, which means it's going to take 80 meters to stop, which is why you hear so many warnings about, like, you know, how just a little bit faster can cause a lot more danger, right? You might think like, oh, I'm going twice as fast, it'll take me twice the distance to stop. When actually it takes 4 times the distance to stop, and that matters like for every little increase in speed, right? It's not just an additive effect in braking distance, it's a multiplicative effect. So as you go faster, it's harder and harder to get the car to come to rest because of all the additional kinetic energy, okay? Questions about that little process there? Work kinetic energy theorem will solve most. What's that?
Where'd you get the coefficient for?
Coefficient 4 is coming from the fact that we're putting 2v in here and squaring it.
Wait, 2 times the velocity would be 120. 120 squared, wouldn't that be like 24 or 144,000?
Well, compare 60 squared and 120 squared. Whatever that answer is 4 times bigger.
Okay.
So 4 times the amount of kinetic energy. Got to have a 4 over here. I can only get that from the delta x because the braking is the same.
Is it always 4 times if the speeds are twice as fast? Is it always 4 times?
Yeah. Yep. At all speeds. Okay. Here's something that you might want to just calculate though. Car starts from rest, it goes to 30, and then goes from 30 to 60. Which one of those changes in velocity takes more energy? The easiest way to do that is just make up a mass and just calculate it and see what happens.
Wait, no change in direction?
Mm-hmm. When you think you have the answer, raise a 1, 2, or 3 indicator.
Oh yeah.
Numbers starting to happen. And I see a few votes out there. It might go against your intuition because of the square that's in there. You might think it's the same change in velocity, same change in kinetic energy. But the squared kind of screws all that up. try some numbers, you should find that that change is larger than the 0 to 30 change. It takes more energy to change the same difference in velocity at higher velocities than at lower velocities, okay? The squared and the kinetic energy fools people, right? Just calculate it and see for yourself. So, we're skipping a few of these. We don't care about those because I got 2 slides left in this chapter, and that'll give us enough time to do part of the first slide of chapter 8, but we're not going to do much in chapter 8 today, okay? So you may remember, if you look back at the previous slides, everything was about a constant force. In other words, we had something that maybe could be graphed like this. If I had a constant force and I graphed the force versus the position, well, then I have a force that's just flat. Whatever it is, it's just staying the same the entire time. So maybe this is you deciding to move a box along the ground and you're like, yay, constant force. So you just keep pushing like this. Fantastic. That was easy, not a problem. Okay? Constant force, it just stays the same the entire time. Well, I want you to notice something. In this particular case, remember that work is force times displacement, and we're going to say in this particular case that force is in the same direction as the displacement, just to make things somewhat simple. And these are the 2 axes that I have, right? I've got x on one and force on the other, and those are the 2 things that are in the equation. So let's say that maybe my object starts here and goes over to this other position x, such that this is the delta x, the change in position. In that particular case, if I just find this area, that's the area of just a box, so that's going to just be base times height, if you want to think about it that way. The base is delta x, and the height is the force, or force delta x, which is the work. That area under the curve of the force versus position graph is the amount of work that's done. Okay, so I'm going to make a little note of that. Work is the area under the curve for force versus x graph. That general idea will apply whether it's constant force, variable force, or any sort of weird force. It works for all of those cases. So let's say that instead we have a variable force that maybe looks like this. Force, here's position, and maybe this time the force starts out okay, but then goes, yeah, and then maybe, this is your very unreliable friend who helps you move, okay? Instead of a good friend, which would be like, let's move the box. Yay, we moved the box. This is your friend who's like, I'll help you move the box. Maybe your friend is drunk. I don't know, because it looks like the force kind of dies there at the end. Your friend just passed out, okay, not applying any force. So the force is all over the place. As the box moves to new positions, well, the force is changing. There's different amounts of force. However, the same rule still applies. It's just harder to calculate. If I wanted to find how much work is done moving the box from here to here with a delta x, if I can find this area once again, then I've found the amount of work done by your very sad friend. And we're not going to do much with it in this class at all, but I want you to be aware of how this would work. If we were to essentially take this and break it up into a bunch of really, really skinny rectangles. Yeah, you know where I'm going. Yeah. And zoom in, like maybe from here to here. If I make that really infinitesimally small, we could call that dx instead of delta x. And if I make it small enough then over that tiny little displacement, the force doesn't change. So it's almost like I'm taking a variable force and making it a bunch of little constant forces, but from one instant to the next, it's a different constant force, okay? So you can imagine right here is some value for the force. So I can do force times delta x, and that gives me like this area, which is part of it. So F times delta x gives me a little bit of the work. And then if we could just add up all of those rectangles, I'm going to get all the work that's done. So what we're saying is that work is the integral from a starting position to a final position of F times dx. The thing that you need is a function for F. I need to know an equation for this graph that I drew, which clearly, that one's going to be a mess, okay? But you can imagine maybe simpler graphs, and if you happen to know the equation for it, you can plug it into that equation, do the integral, and it'll take the area under the curve for you. We're going to keep it a little simpler than that, okay? So for instance, you might imagine a variable force that's, where do I want to put this? Let's find a little space down here. Ooh. A variable force that at least has constant parts. So you might imagine a force that looks like this. Force X. Maybe it starts constant here, and then maybe it decides to decrease for a little while, and then maybe it's constant again at a lower level. And I don't know why I can't draw straight lines. That's a variable force. Okay? It just turns out that the integration really doesn't need to be done because I can just use this area under the curve idea. And the thing is, like, well, there's a box, and then there's like a box there, and then there's a triangle. If I can just find those areas geometrically, we're done. We don't have to think about it anymore. Okay? So again, the area still applies. You can just break it up into little parts. You might see some stuff kind of like that in the homework, so you can find the work that way. But it turns out there is a variable force that's already known by us. So let's call this, did I just delete something over there? I think I did. Go back. Maybe I didn't, okay. We have one known variable force that we've been using, and we have an equation for it. Think back to your list of special forces. One of them is a function of x. Which one was it? Only one. One of them had an x in the equation. Friction is mu times the normal force. No x there. Which one had x? Maybe some of these people passing by can help. They don't look like they want to help. Nobody does. This one's got a dog. Very happy with the dog. Yeah. Which one was a function of x? Which force? Gravity? Tension? Normal? Friction? What else you got? Spring. Spring. Remember the spring force, if I just look at the magnitude, is k times x. That's a variable force. It is not a constant force. It depends on how much x you have. Think about stretching a spring, right? You stretch it a little bit, it's like, please don't do that. You stretch it a little more, it's like, I really wish you wouldn't do that. You stretch it more, like as you pull it farther and farther apart, it pulls back harder and harder, meaning it gets more difficult for you to stretch. You can't just like infinitely stretch it without any problem, right? The more you stretch it, the more x, the more force you have, okay? So if I were to graph that force, it turns out that's just a linear equation with a slope. So it looks something just like that. Kx. The slope is the spring constant, okay? It has 0 y-intercept. That is a variable force with an equation we already know. You could find the area under the curve by plugging it up into that integral if you wanted to. If you wanted to. Maybe you want to later just to see if you can do it, if you can test yourself.
Or we can look at this and say, that looks an awful lot like a triangle. I can find the area of a triangle, right? So the area here is 1/2 base times height. The base is x, and the height is the spring force, which is 1/2 x times kx, which is 1/2 kx squared. This is the work done by the spring force. If you go up here and plug in kx into that equation, we have an equation for that force. Do the integral, you should get the exact same thing. Okay? Test yourself with that and see if you agree. So, I know it's hilarious, right? That those two things would work out that way. Yeah, I agree. It is funny. It's odd, maybe unexpected, or maybe very expected. All right? Constant force is what we had before. Variable force is found by that integral, which is really just the area under the curve. That's what you need to take away from this slide. Okay? Yes?
So, when you stretch a string,
Spring.
when you stretch a string too far, and it doesn't, like it can't retain its original shape, can you represent that graphically?
Yes. If we had a spring that was stretched too far, it would probably look something like this. It'd be like, yay, I'm going to linearly increase my force, and then all of a sudden, like something weird happens, meaning that you might even feel like as you stretch it, you feel it break, and now it's not pulling as hard on you. The force kind of drops, and now it doesn't even have enough force to pull it all the way back to equilibrium again. We're not going to worry about that. Springs that you would say that you've surpassed the elastic limit of the spring. The elastic limit being how far you can stretch it and still get it back to where it was before, but you're not going to have to worry about that. Good question. Anybody else before we do this last slide in chapter 7? Okay. The last slide is almost nothing. We're going to do very little with it in this class. I'm going to give you 2 equations. You're going to see a little bit more about this in Physics 230, but you should know or be aware of it right now. This concept of power. Power is a measurement of how fast the work is being done. Not how much work is being done, but how quickly it happens. Meaning that power is work divided by how much time that takes. Work divided by time. If you look at the units, we have joules in the numerator, seconds in the denominator. This is known as the watt, which isn't confusing at all that we have a symbol W for the unit of power when work is already given just the symbol W. So there's W's all over the place. Just be careful. W is work. W is also the unit of power. Okay? No, they're both just capital. I mean, sometimes I see work expressed as a lowercase w, but we're just using capital for both. Okay? Work divided by time is power. Or, one other way to look at this. Let's plug in our equation for work. F delta x. And then that thing I circled, what is that? Yeah, that's velocity. So force times velocity is also power, which I think makes sense, right? If I'm applying a force, pushing the box slowly versus doing the work quickly by pushing it fast, well, I'm doing the work at a different rate. I'm doing the work faster if I have more velocity, okay? That's all you need for this slide. That's the end of chapter 7. Yay, we're done with another chapter. Congratulations, everybody.
How many more chapters?
All of them. I don't know. I really have no idea. 5-ish maybe?
Physics 230 is a continuation of where we left off at 220, right?
Yeah. So there are places we need to get to, because who in the world knows who will be professors for the next class?
Are you teaching 230 now?
I don't know. Nothing is known at this point. They've just started dealing with scheduling. So you could have anybody and they might be like, hey, you covered all these chapters, right? And
And you might be like, no, and that'd be sad. So we do have quite a few more that we have to get to if at all possible. So let's jump to chapter 8. And if it helps at all, the fact that you're like, oh, starting a new chapter is really hard when there's 19 minutes left in class, and you're like, oh, can't we just go eat lunch? You're hungry, aren't you? A little bit hungry. We're gonna go to right here, and then we're gonna stop, however long that takes. So it'll probably be a few minutes early if I had to guess. Okay, that's as far as we're going in chapter 8, which will get us to exactly where I was in the morning, earlier morning section. Okay, so chapter 8 is a continuation of 7. It's all the same stuff. We're just going to go a little deeper. 7 and 8 are kind of like one chapter that they just decided was too long and split in two. All right. So to start this chapter, we have to talk about 2 broad categories that all forces fit into. And if you remember back when I first talked about forces, I gave you 2 categories there as well. You can categorize forces by being a contact force or an action at a distance force. This is another system of categorization. Okay. All forces are either a conservative force, or I really expect the next slide to be liberal force. It just feels like that should be the opposite for some reason. I don't know why. All right, but instead we have conservative forces and non-conservative forces. All right, all forces go into one of these 2 categories, and it turns out all of those special forces we have so far, all 5 of them, they go in one or the other. These are not new types of forces. They are categories of forces, all right? So first of all, conservative forces. When you see this word conservative, don't think politics. Think conservation. Think saving the planet. Think trying to keep everything just like it was before. Think not losing stuff, all right? Think about recycling. Think about that blue can that's over there. When we talk about conservative forces, what we mean is conservation. We mean that whatever energy you have gets stored, not wasted, in a way that I can use it later. So you can see the definition says that if it's a conservative force that's doing the work, then whatever energy comes from that work is stored in a way that I can get it back. It doesn't get thrown away. Thrown away work and energy kind of lives over on this next slide. Okay? So any force that stores the energy for release later is considered a conservative force. So that can be released later might get you to start thinking about potential energy. It's energy that's just waiting to get out, okay, as we talked about in the last chapter. As we get later into this chapter, we're going to discuss a few different types of potential energy that's based on different conservative forces, okay? So let me describe this with a bit of an example. I don't know if I'd really call it an example, but maybe a little bit. Let's just say we're going to lift a box at constant velocity. So we have a box. There it is. We're going to lift it in this direction, a certain displacement. As I lift the box, there are 2 forces acting on the box. What are they? Exactly. As I lift the box, name one of the forces acting on the box. Gravity. And a normal force. Good. Gravity's down. Normal force is up. So let's do this.
Air resistance is not a force, is it?
It is, but it's one we ignore in this class. It's complicated, to say the least. Okay, you're done, all right? Sum of forces in the y direction. So I've got a normal force that's up, a gravitational force that's down. What's the acceleration? Constant velocity means the acceleration is 0. So I can say that the normal force is equal to the gravitational force, which is mg, for this particular case. Okay, the normal force, the force that I'm applying to lift the box, is equal to the gravitational force, which means that its motion stays constant. It doesn't speed up, doesn't slow down. So let's talk a little bit about, first of all, the work
being done by the normal force in this problem? The work being done by the normal force. First of all, notice the normal force points up, the displacement points up. The normal force is doing positive work. It's normal force times delta y. And we just said in this problem the normal force is mg. So mg delta y is how much work is being done by the normal force. If you think about it, I'm applying a force this way, putting energy into the box, right? Maybe it wasn't moving, now it is. Maybe now I'm trying to make it speed up, but it's not speeding up. Its motion isn't changing. Why is it not changing? It's because gravity is there as well. So there's work being done by the gravitational force. Notice the gravitational force and the displacement point in opposite directions. So it's going to be negative work, Fg times delta y. So that's negative mg delta y. So one way to look at these two forces and how much work they're doing, you could say that I do work on the box. I'm putting energy in, okay? So let's say I'm doing positive work on the box while gravity does equal negative work on the box. I'm doing positive work on the box, I'm putting energy in. Simultaneously, gravity's doing the exact same amount of work and sucking that energy out. Okay? That means the energy isn't changing. The energy of the box isn't changing. Which means that if I add these together and just found work total is 0. Right? Same amount of positive and negative. If the work total is 0, then the change in kinetic energy is 0. And that's true because the velocity is constant. It's not changing. It's not speeding up or slowing down. So everything about this agrees with what we had before. But let me put one additional point on this work being done by gravity. So I do work and put energy into the box. Gravity does work and takes energy out, and it puts it somewhere, okay? So we could say, and stores it for later. It's almost like gravity, the force gravity vector, like has a backpack. It takes energy out of things and just puts it in the backpack. And it's like, yeah, later, we'll get back to that. We're going to do something with that later. I'm not going to waste the effort that that person put in into lifting the box. Like that, maybe it was a heavy box. They're like, and lifted the box, right? I don't want to waste that effort, that energy that got put in. I'm not going to let the box keep it. I'm going to take it out and store it for later, but I'm not going to waste it. I'm going to conserve it. I'm going to keep it for later. And if you think about it, you know that there's energy waiting to be released now, right? I did work to lift this here, and all that's keeping it from falling is the fact that I'm still applying this force upwards, right? All I have to do is remove that, and gravity says, ha ha ha, and throws the energy right back into the object and says, go to the ground. Yeah, and then it becomes kinetic energy once again. So gravity doesn't waste the effort of lifting. Instead, it'll put the energy right back in as soon as I remove that external force. It saves the energy for later use. Are we okay so far? Okay. The second one is relatively quick, and then we'll be done for the day, and I'll see you all on Thursday. And that is the idea that a conservative force does 0 work around a closed path. By a closed path, we simply mean the same starting and ending point. So let's say that once again, we take a box and we're going to lift it. So it goes up this way. And let's say that now we take the box and take it straight back down. Same starting and ending point, right? I go up, I go right back down. Exactly to where it started. There is a gravitational force that's down on the box the entire time. So you might imagine that, well, as the box goes up, these two vectors are pointing in the opposite direction. It's going to do negative work.
equal to mg delta y. And when it comes back down, now the gravitational force and the displacement are in the same direction. It does positive work. Same amounts, one's positive, one's negative. If I add those up, I'm going to get 0. Okay? Because of that, we can say that gravity is a conservative force. If I get back to the end and the total's not 0, something weird happened. Some of my work, some of the effort and energy went somewhere else. It didn't all get stored. Maybe some seeped away into air resistance or something, some other kind of thing that we're going to deal with a little bit later on. As long as you have 0 total work done by the force when it gets back to where it started, then that's a conservative force, all right? We're going to deal with the third one of these on Thursday, because today is Tuesday. Yes, I know where I am in the week. I will see you all then. Goodbye. Farewell. Have a good Wednesday and a good rest of the Tuesday and a good Thursday morning. Come back and see me Thursday. Miss me. Try to. Forget about me completely over the next 2 days. That's fine too. I'm just going to keep talking like this. Why not?
Oh, I forgot to ask, what room is your office?
What room? That is Thornton 384, I think that is. No, 3.
Is it close to the entrance?
328.
It's close to the entrance.
Yeah,
right?
it's like 3 doors down.
Okay, yeah, I know where you're from. I saw you walking out.
Okay, cool.
Teaching 2:30 this spring.
I don't